Hello, my name is Innokentii Sennovskii. I'll be giving a talk, Wake Up Neo, Detecting Virtualization through Speculative Execution. A little bit about myself. I graduated this year from National Russian Nuclear University MIFI with an information security degree. I'm a reverse engineering specialist at Byzone LLC. I'm generally interested in applied cryptography, reverse engineering, hardware attacks, and especially side channel attacks. And the talk I'm giving is based on my discovery of Spectre Variant 3A. If you have any questions about the talk or want to contact me on another unrelated manner, you can use this email or write to me on Twitter. So let's dive in. Modern CPU attacks on the x86 architecture go back from the first Intel 8086 processor. The CPUs back in the day were much less complex. For example, Intel 8086 used just 16-bit registers. You could only address 1 megabyte of memory through the use of segments. There were no memory protections. The only thing you could use was real mode. The feature size was just 3 micrometers. But at that time already they had a 6-byte prefetch so that you could load the next instruction while the current one was executing. And there was no and there was even no FPU, or floating point unit inside, so you had to buy a separate coprocessor just to operate on floating point numbers. Obviously, the CPUs had to evolve to be able to manage and compute modern tasks. One of the first things to come was the floating point unit, which is now omnipresent. We have an increased register size. Nowadays, regular registers are up to 64 bits. Modern CPUs also have implemented protected mode and paging, which allow for greater manipulation of memory space and allow multi-user environments to operate. We have a single instruction, multiple data extensions, which allow the user to execute simultaneous tasks on the same sets of data without using the same instructions. And we even have system management mode for tasks specific to manipulation of hardware and precise management of power. Obviously, the CPUs today wouldn't be so welcome and so used if those were the only parts of the evolution. The CPUs have become much more efficient. They can process more data, they're faster. And the straightforward ways to increase this performance were usually increasing the frequency so that more operation could be computed in a single second, and increasing the cores so that you could split the operation into several cores and perform tasks simultaneously. So basically just more power. But this approach has its limits. First, one of the bottlenecks of CPU performance is memory access time. Obviously, the CPU has to retrieve the data somehow, and the data isn't stored on the CPU itself. It has to access RAM. Memory access is usually quite slow in terms of CPU cycles. So that's one of the limits. Obviously, increasing the frequency also decreases energy efficiency and can even overheat the CPU. Finally, there are basic laws of nature. For example, if we try to operate a CPU at 500 gigahertz, we would run into the problems with Einstein's theory of relativity. We just wouldn't be able to do that. So we had to imagine new ways of increasing performance without resorting to increasing frequency and increasing the number of cores. Such clever solutions include cache, translation look-aside buffers, hyperthreading, branch prediction, and return stack buffers. Cache is a mechanism created to decrease the number of memory accesses from the CPU. Basically, what it does is save data from previous accesses on the CPU so that the next time it doesn't have to go through to RAM, get the data, and retrieve it back to the CPU. In Intel processors, there are 3 levels of cache, level 3, 2, and 1. Level 3 is the same for all cores. Levels 2 and 1 are specific to each core. And level 1 is also split into data cache and instruction cache, which don't overlap. They decrease in size from level 3 to level 1, and level 1 is much faster than level 3 and level 2. Also, we have to remember that cache is split into cache lines, which means that if you retrieve 1 byte of data from RAM, 16 bytes of data are actually placed on cache. For example, if you retrieve the first byte from a particular page, the following 15 bytes will also be saved. So basically, cache operates kind of like trying to look up an entry in an encyclopedia. If you want to look it up the first time, you have to go to the library, check out the book, and bring it home. The next time you try to read the same entry, you can just get it on your bookshelf at home, and basically all your family members can get it too. And the last level of cache, the level 1 cache, is when you have the book beside you and you just have to stretch your hand, take it, and look. Translation look-aside buffers are kind of like cache for paging. Paging is the mechanism which is used to translate virtual addresses into physical address space. The problem with modern CPUs and with multi-user environments is that you can't just use linear mapping of linear paging. You have to manage the pages that are allocated for each user. You have to load different pages, and you have to set up specific addresses. For example, the address space for kernel and for user mode is split. So each access of a particular set of data requires you first to go through the paging. So you have to look the parts of the virtual address in several pages, resulting in 4 free accesses before you actually get the data, which means that the time of accessing the data without cache is 5 times slower than if we just use physical addresses. To cope with that, modern CPUs have these translation look-aside buffers, which save the translation from virtual address to physical address, or at least some steps of it. For example, it can cache page table entries or page directory entries. One of the features with modern CPUs is that there are many different computing units. You have, as I previously said, single instruction, multiple data effects. You have floating point units. You have the general register operations, which are used to compute different tasks. The problem with previous CPUs, for example with Pentiums, were that certain instructions there was a strong ordering of instructions that the CPU executed. So if an instruction was going after a certain instruction, it had to be executed in that particular order. But at some point, Intel decided that, well, what's the problem with splitting the execution into several parts? For example, you can preemptively execute something on an unused part of the CPU. For example, if you are operating on general registers, you can at the same time compute a future task on the SIMD extensions. So we got out of order execution. Well, the problem with out-of-order execution was to decide what to execute. And for that purpose, Intel implemented several techniques. One is branch prediction. Branch prediction collects statistics, collects information about previously executed branches, previous jumps, previous calls, and from that statistics it decides when it meets similar conditions that probably the next branch, the next jump is going to go to this location. So while we are executing our current task, we can start on that task with a different part of the CPU. Return stack buffers contain up to 16 return locations for previous calls. So basically, each time you use a call in Intel x86 or Intel x64, the location to which the function you are calling has to return is cached in this return stack buffer, which is on the CPU. And if the execution takes a long time, then the CPU starts to compute the data and execute the instructions after the actual call, getting the information which it has to execute from return stack buffer. This is what's called speculative execution. Now, speculative execution is a little bit like standing in a queue for ice cream. For example, you have two flavors, A and B. You and your friends are waiting and one of you decides to go and get drinks. The problem is that a particular flavor of ice cream only works with a particular flavor of drink. The guy gets the drink, then you meet and you see that you mismatched. You got the flavor of ice cream which doesn't work with this particular drink. What you have to do after that is get the drink you really need. So basically you discard the thing you got before and do it anew. That's how speculative execution works if there are some problems. For example, if you don't actually return to the predetermined place, then it just discards the data that was computed. It performs all the checks and you have to do everything anew. So speculative execution wouldn't be as important today and as problematic today if there weren't a cache side channel. Side channel is a general reveal information about a process that without using the process entry and exit points. It uses a previously unintended way of getting information, especially sensitive information about the process, through irregular means. Some common side channels in the CPU and previously discovered side channels include the cross-VM prime plus probe attack on RSA square and multiply algorithm, IST table flush and reload attack, and a few more. But for the most part, this kind of attack was used only on cryptography. Since cryptography always has sensitive data, for example, the key, and up to a certain point, cryptography, which was executed in a shared environment, was perceived to be quite secure before these kind of attacks came up. So the cache side channel is performed through observing the states of cache lines. For example, if you access a certain location and a cache line is committed to memory, is committed to the CPU, after that you can discern whether the cache line was committed. There are several techniques for abusing side channels. One is flush and reload. Evict plus time and flush plus flush are a variation of flush plus reload attack, and there is also prime plus probe. I'll be going into more detail on flush plus reload since I use it in my technique. So flush plus reload takes a contiguous page region. For example, the usual way is 256 4 kilobyte pages. Then it flushes all the cache lines from these pages, and triggers the execution of the observed function or process, or just waits for it to execute. The process accesses the memory in some way, for example, this continuous range, and then you can time the access to each page to retrieve some data from it. Then, well, depending on what kind of process it is, you can get some sensitive value, so you basically get profit. So how speculative execution plus cache side channel work? First, you have to serialize the execution so that all store and flush and load and flushing operations complete. We use memory fence operation in the Intel CPU for that. Then we call a specific function called herring, which executes many instructions on the SIMD part of the CPU. Then in the end of the herring, we actually switch the return address so that it doesn't return to line 3 here. So everything from line 3 is actually executed speculatively and preemptively. We place value 5 into the RUX register, the RX register. We then multiply RX by 4096 to align it to a page, and we do a speculative read from this page. All the results of this read are obviously discarded, but there is still a change in the microarchitectural state. So we can see on the right side that the fifth region actually lights up because the access time to the fifth region after this function executes is much lower than for any other page in this particular region. So obviously we can send some data through speculative execution, and there have already been several solutions which store and access privileged data. Well, the case in point being meltdown. Is there anything else we can retrieve from speculative execution? Well, first we have to ask ourselves: can we execute everything speculatively? Obviously, there are some limits. For example, we can't execute interrupts. For example, the int3 breakpoint, which is commonly used for debugging, can be executed speculatively. Some privileged instructions, for example, RDMSR, which is used to read model-specific registers, can't be executed in user mode. It is only executable in current privilege level being 0. Also, well, many other instructions which lead to context switches can't be executed since the CPU doesn't know how to handle them speculatively. So what can we do with this information? Basically, malware, for example, or some DRM solution, digital right management solutions, can use this to detect software breakpoints, but they're usually easily detectable anyway, just through reading the memory and checking if anything has changed. We can check for hardware breakpoints, which are usually quite hard to detect since they leave no trace in the readable memory, and are just set by setting the registers DR0 through DR7 in the kernel mode. And the most interesting of all is we can detect page breakpoints, which are usually quite hard to detect. For example, I'll show right now how to detect hardware breakpoints. Let's try, yeah. So we have a simple program here, which creates a continuous memory range. Then it uses a speculate function, which calls herring, and then executes something after that with accessing a page from a certain location, basically from region 20. If we execute it as it is now, we can see there were no cache misses. Basically, we see that speculative region is not debugged, and through the use of monitoring which pages were actually accessed, we see that the speculative region accessed region number 20 in hex most of the time. There were just 2 misses, which is negligible. Basically, anything under 1% is okay. Now let's try to set a breakpoint. And let's set a hardware one at that. So let's try to execute the same function. As we see, the breakpoint wasn't hit since it's in speculative region, and the debugger doesn't know anything about it, actually. It doesn't think that this portion of memory was executed. And what did we get? We see that the page misses are all over. We have actually most of the accesses are cache misses, which didn't go in the specified region. So we can determine that there was a hardware breakpoint on execution. Now let's talk about virtualization. Virtualization is used on servers. It is used by researchers or programmers to for a secure environment and to run programs, for example, in a different operating system. But what most interests us is that it's used for security purposes, for example, in virtualization sandboxes. Basically, hardware virtualization in case of Intel virtual machine extensions split the execution into 2 classes of software: the virtual machine monitor and the guest software. The virtual machine monitor actually initializes virtual machine extensions. Then it sets up and initializes the guests. It can catch the guest when a certain condition is met and stop, and the execution of a guest is stopped. This condition is called a VM exit. After that, it controls the state of the guest and can change the flow of execution. Basically, the virtual machine monitor controls the guest completely. And after that, it can reinitialize or continue the state of the guest so that the guest gets executed. Guest software, on the other hand, operates as if there is no virtualization. Obviously, some hypervisors show guests that it is virtualized, so that it can perform tasks better. But for example, sandbox virtualization usually does everything so it can be detected by the guest, so that malware can detect that it is being virtualized. Also, guest gives control back to virtual machine monitor all the time. So basically, if anything suspicious, anything out of the ordinary happens, for example, a context switch, it gives control back to virtual machine monitor. So the standard operation is virtual machine monitor starting with vmx on, then launching the guest with VM entry, then it receives a VM exit from guest. So the guest at this point stops, has its execution stopped, and after that, virtual machine monitor can launch the 0 guest new or start a new guest, and in the end, it can switch off virtualization completely by using VMX off. VMX is effectively a context switch from guest to VMM. It can happen under several conditions. For example, on certain breakpoints, on instructions which are computed by the virtual machine monitor, for example, CPU IDs, so that the virtual machine monitor can present a different environment to the guest than the one which it's actually executed on. For example, you can substitute the Intel's standard Intel CPU code from CPU ID to AMD's, and the guest won't actually know that it's executing on an Intel CPU. VMM also receives all the information about the current state of the guest when the guest when a VM exit happens. So all register states, all the states of memory, which operation is currently executing, everything. So there were several ways to detect hardware virtualization. One of the most obvious ones is timing VM exiting instructions through the use of RDTC. And for that particular problem, Intel came up with a solution. Basically, RDTC became an instruction which is also causing a VM exit. And you can change the actual values which are returned so that you can fake execution without virtualization. You just decrease the RDTC value each time. So this particular technique is not quite useful nowadays against sandbox virtualization. Then there is also detecting microarchitectural changes. For example, if you try to, return stack buffer gets flushed when a VM exit is committed, because the execution flow switches back to virtual machine monitor, and every piece of data which was stored is in return stack buffer is actually overwritten. So when you return, the returns are actually slower than if there was no virtualization at all. These are quite interesting, but there are some problems with that. So timing VM exit has several problems. It's obvious to a sandbox. The values can be manipulated, and it also can be evaded with blue chicken-like techniques. You can read John Rutkovska's research on this part. Basically, sometimes you can just unload virtualization or unload RDTC catching on VM exits, and it would allow you to evade such techniques. And microarchitectural change detection, while being quite precise, has a single problem, that it has to be executed in current privilege level 0. Basically, this means that malware needs first to go to kernel mode, which is not the case with most malware nowadays, and only then it can check that it's being debugged or traced. So that's a problem. But this particular technique allows you to detect virtualization through microarchitectural changes in RIN-free. What we do is place an RDTSC instruction in the speculative region, and then base memory accesses for side channel on the value which was returned. So here we get the standard mfence instruction, then the code which triggers speculative execution. Then we get RDTSC, which returns data to registers EDX and EAX. Then we cut some of the data out so that we only have the last 4 bits. We need to collect some of those bits so that speculative execution can't go past RDTC if it's not executed. We add OX50 to racks so that we predetermine a region which is going to be accessed, and then we align it to page border and read from there. So basically, we execute one of the VM exit instructions, modify the results, and read from the page. This is enough, since there are now 2 cases. If we are not executing in a virtual environment, then RDTC will work. It will be executed speculatively. There are no problems. And if we're executed in a virtual environment, then RDTC can't be executed speculatively at all. The problem being that the CPU doesn't know how to, it knows how to execute RDTC, but it would take too much time to perform a context switch. So it decides not to execute RDTC and just wait for the execution to serialize. Then we see 2 completely different pictures. The one on the left is Um, when RDTSC is executed speculatively. We commit to a certain region, basically the fifth region which was predetermined, and then we know that we are not executed speculatively. And the one on the right is the case with the virtual machine. Since RDSC instruction can be executed, we can't. There is no side channel back to the memory, and all the accesses, all the quickest pages over, for example, 1,000 tries or 10,000 tries are evenly spread over the area. So I'll show a demo now. Basically, the terminal on the left is operating in a non-virtualized environment in the VMM, and the Kali virtual machine on the right operates under virtualization. So first, let's create the ELF. Let me show you that all the files are the same. We can see that, well, those are the same files. This is the same actual executable. This is just a shared folder. Now let's try to execute the virtualization check in a non-virtualized environment. As we can see, only 10 out of 10,000 tries actually missed the cache area, which was predetermined. So we see that RDTC is not virtualized, it is executed speculatively, there is no problem. Now let's try to execute the same program under virtualization. First, you saw how it took a little bit more time. That's because there was no cache, so basically that was one of the differences. The second one is that obviously RDTSC is not executed speculatively, so we have lots of cache misses. What's the problem with this? One, you can reliably detect virtualization from RIN-free through speculative execution. And you can do it simply by checking whether the region is the same. So you have two cases which I showed. Basically, a small amount of cache misses under 1%, or a large one where almost all of the cases return a cache miss. And that's quite simple. For example, if you created a simple binary check, then the reverse engineer in the end would be able to detect this, while a sandboxing solution wouldn't probably be able to detect this automatically. Still, that wouldn't be a problem for reverse engineer. He would just flip the switch, flip the jump or the result of the test, and would still get an unpacked solution. For example, if there is a packed malware binary which uses this to detect virtualization. The problem with speculative execution based hypervisor detection is that it's the first of its kind which can actually compute some data based on the fact whether there is virtualization or not. For example, let's go back a bit. No, okay. So basically, the problem is that you can place anything in the speculative region. So you can place anything in the speculative region. For example, after RDTSC, you can place some instructions which compute different data based on the predetermined data, and then collect the results of that execution. You can then compute a key used for unpacking from that data, and that would be a big problem for a researcher. What's more is that under certain conditions, speculative execution, when there is no side channel, has so-called zero bias. It means that when you're timing pages to determine which page has the fastest access, most of the values will be biased to zero page, since all of them can be the fastest, but they can also have the same access time. Which means that you can create two separate sets of data for unpacking, two separate sets of keys. One key which is actually computed with speculative execution during if there is a side channel, and the second set which is computed with some tampering if there is no side channel. It will be biased to zero, and you can still decrypt meaningful data through the use of this key. And this cunning scheme would enable you to create a completely different solution, for example, to unpack some kind of adware or some kind of game instead of actual malware, and trick a reverse engineer into flagging your executable, which actually has malware as benign. So the conclusions are: obviously, speculative execution can be used to detect virtualization. It can also be a great headache for researchers and reverse engineers, since there would be a lot of problems and it would be quite hard to analyze, as speculative execution can be debugged. There is no way to debug it, since it's not executed in regular software terms. Also, if it's used by mass malware, it can be a great problem for many automatic sandboxes, and it can actually lead to many false positive for future detections. If you're interested in trying it yourself, you can look up the proof of concepts on GitHub on this link.